Hello CIO world, and welcome to the introductory lecture of piping system design. In this lecture we will cover the basics of piping from the concept of nominal diameters, wall thicknesses, etc., so that you will be able to determine the internal and external diameters of pipes and tubes. We will also have a look at various pipe classifications based on concepts like serial numbers and piping schedules, and also consider physical limitations of piping, such as pressure and temperature. We will also look at the basics of translating designs, piping system designs, into flow diagrams, and what the various symbols will mean. And lastly, we'll also learn how to draw process flow diagrams from a description of a process, and also use things like a P01, a process flow diagram that is specific to the piping and the instrumentation for that process. On a side note, you can also follow your piping system design handbook as we go along in the slides, as I'll put up the corresponding page numbers to indicate which slide is correlating to what page. Right, so let's talk piping. A Google search into what is defined as a pipe and a tube may be quite difficult. What you need to remember is that these two terms are generally used interchangeably, but came into use to distinguish surface roughness, for example, and how this is associated to frictional losses through the pipe. For our definitions, we will take a pipe to mean any conduit that has a specific surface roughness that contributes to the energy calculations that we will be making in Chapter 4 and onwards. Tubes, on the other hand, tend to have very smooth surfaces with a low surface roughness. So the difference here becomes more of how the pipes were manufactured, and we'll go into this shortly. Let's turn our attention for now to Appendix C1. In the table, as you see, you will see a list of descriptions of various materials of construction for pipes and tubes, such as concrete and riveted pipe and cast iron, etc. Note that the roughness, which is given by the symbol epsilon, is given in millimeter. Be very careful when using this, as oftentimes it is forgotten to convert this to meter if we are using our diameters in meter as well when calculating the frictional losses inside pipes. Notice that for glass, for example, the roughness is negligible, while the drawn tubing such as copper and brass and plastic-based materials like PVC piping and high-density polyethylene piping, the roughness is quite low. Sometimes we would also actually want to line our pipes with glass, for example, when using highly reactive streams, or we would like to line the pipes with polytetrafluoroethylene or polyvinylidene fluoride when working with streams that contain very reactive materials like fluorides. South Africa has the third largest fluorospar reserves in the world, so we would typically want to operate these plants that refine such materials with specific piping systems that can withstand the corrosive nature of these things. Also take note that you can find some additional information in reference books such as Perry's Chemical Engineer's Handbook, 7th, 8th, 9th, or whatever edition we are on now. Okay, so why do pipes have different roughnesses? Well, surface roughness comes about by how the pipe was manufactured. So think about the roughness of concrete. It is made up of little bits of sand glued together, and so the material of construction usually dictates the roughness. Just as, if you have a material made out of sand, it's going to be very, very rough. Right, but one other consideration is how pipes and tubes are being manufactured. So let's consider steel piping, for example. So first off, the steel is heated. Maybe the steel comes in from a recycling plant. You first remove all the non-ferrous materials from the ferrous materials. Usually you do this with a electromagnet that you charge and then discharge. So you pick up all your iron and you discharge it again, and then the iron or the steel will fall into a vat or a hopper. All right. And then the steel is heated to very high temperatures using an arc furnace, which operates above 1000 degrees Celsius to melt the steel before you add additives. You can usually add the additives during the ladling. So ladling is where you pour the molten steel into a ladle. It's like into a massive vessel containing maybe, 60 ton of steel. These additives will then prevent oxidation, scaling, and also improve the overall physical properties of the steel that you're making, and also change the grade of steel that you're making. The large ladle then is used to carry the molten steel away to be casted. During casting, we cast the steel into billets or blooms, and these are steel sections that are formed into rectangular shapes. And these are just made so that it's easy to store, pack, and handle them. So let's move on to the next slide, and then you can see one of these billets being formed. Right. So during this stage, what we tend to do is heat up the billets again in a furnace. We don't want to melt it; we just want to heat it in order to roll it and lengthen it into cylinders. This is followed by milling, where cylinders are bored into pipes. So we actually make a hole in the pipe. These pipes are further worked into the desired diameters. Just to give you an example, a 3 millimeter diameter pipe is first drawn from a 32 millimeter diameter pipe by literally pulling with immense force on this pipe to reduce its size. So think about taking a piece of bubblegum out of your mouth and pulling it out into strands. I like eating bubblegum. I also like swallowing it. So I won't recommend you pull it out of your mouth and then stick it somewhere. Just, swallow it and let it go through your digestive system, all happy. It will come out eventually. So in any case, if you pull on the bubblegum, you'll notice that the strands become thinner and thinner and thinner. So this is exactly what is being done to these hollowed out pipes to change their pipe diameters. So that's pretty impressive as a manufacturing process. Now, during the manufacturing of these different diameter pipes, through drawing, through pulling on the pipe, the pipes tend to lose some of their physical strength and also become brittle. So in order to reverse this, the pipes are placed back into the furnace, into a different furnace. Usually the furnace is operated continuously in an inert atmosphere to realign the crystal structure within the pipe or within the steel. And this helps to remove those stresses that came into the pipe. And this process is called annealing. So we anneal the steel using heat. We reset the crystal lattice of the steel. So this fabrication process tends to form very rough surfaced pipes. You can imagine. So you can see those pipes lying there on the rollers. They don't look very, very shiny, so you can imagine how rough they are. So these pipes would require further refining in order to reduce the surface roughness, but obviously this will cost more money, and we tend to use the pipes therefore as is, unless we really, really do require smooth pipes. But then you're going to pay out of your pocket. Right. Let's talk about plastic. The fabrication of plastic tubes is similar, only in the initial phase of the process compared to steel pipes. The plastic material usually comes in the form of beads or powder. So if I were to buy high-density polyethylene from Sasol, from the wax section, I would get the bag sent to me, maybe 25 kilo or 50 kilogram bags. And the bags would contain these little beads. I think they're like 1 or 2 millimeters in diameter. I would mix them with any additives like colorants or antioxidants or flame retardants before this as a mixture is hopped into an extruder. The extruder has many heaters running along its side, as well as a very large screw in the middle that both presses and pulls on the mount internally. It's like a big corkscrew almost, but it's um, the threading of the screw is changed so that at one portion there's actually an immense force, like a pushing force, and this force also helps to induce the melt, to melt the plastic and heat it up and keep it hot. And then eventually this melt is pressed through a die. What exits is a fully formed tube. This tube is then checked for any defects. Usually you use something like a laser. You check the tolerances, the wall thickness. Right. This pipe is typically produced with an inherently low surface roughness compared to a steel pipe. All right, so we are now done with talking pipes. Let's go on and talk about valves. Valves are not used only to stop and start fluids, but they're also used to control fluids. Since the fluid comes in various shapes and sizes and phases, and also used in various fashions, we typically require various types of valves to meet our needs and applications. So first off is the gate valve. The gate valve has a gate that opens very much like a gate that you would push and pull closed, push open, push closed. This gate is not swinging. It doesn't swing on a hinge. It opens up and down. It slides through guides. All right. A globe valve is like a big globe. Think of a plug, but now this plug instead is like a ball. It sits onto the seat. The seat has a hole in it where the fluid has to flow, and the globe makes contact with the seat in order to close the path for the fluid so that it can stop the fluid flowing. Obviously, the fluid has to flow around the ball as well. So there's frictional losses that come in, into play depending on the type of valve that you're dealing with. A plug valve has a plug, but the fluid typically has to flow through the plug. There's a bore or a hole drilled through the plug. And so this plug turns open and closed and restricts flow through itself. A ball valve operates in a similar fashion, so you can compare this to a plug valve. But in other words, this just simply has a ball through which a hole is drilled through. Right, so compare this to a globe valve as well as a plug valve. A butterfly valve is a gate valve, except that the plate in question sits in the path of flow. It can be opened and closed by swinging the plate on its axes as shown. And a check valve is a type of one-way valve that opens only when the threshold pressure is reached. And you can also consider what sort of application one would make use of such a valve. I might ask you a very nice question on this, so keep this in mind. The next valve is a diaphragm valve. It uses a flexible diaphragm between the piston and the fluid. Often when you do not want the working bits and parts of the valve to make contact with the fluid because maybe the fluid may damage the valve, you'd often make use of a diaphragm instead. The valve could be made up of a hollow chamber through which you would pass a pneumatic fluid. So the valve would then be pushed downwards by a pneumatic pressure like air. Okay, and then that diaphragm would then close and then restrict the flow of the other fluid, maybe water. Okay. Think very hard about your own valves in your body, and especially those ones that should not work well in public. Okay, those also kind of like diaphragm valves. Anyways, let's move on to see how do we work with valves in design of piping systems. And more specifically, how do we take into account the effects of such equipment on how they affect the overall energy balance of the system? So we'll look at the energy balance for piping systems. I think in chapter 3 and chapter 4 we start developing an understanding of that. But for now, let's turn to our piping system textbooks again and go to the appendices of C3 and C5. In Appendix C3, you will see a description of various types of valves, as well as their applications, as well as the degree of openness. The last column you see on the right is the unitless number that we refer to as LR/D, which is used to determine the equivalent length for each of the types of valves. The equivalent lengths are functions of the diameter. So for each valve that you would use a specific diameter of valve. All right. What is an equivalent length, you may ask? Well, it is the additional length one would need to add to a pipe calculation, theoretically, to factor in any frictional loss that is caused by the valve in question. So consider a fully open globe valve with the stern running perpendicular to the run and with no obstruction. It has an LR/D of 340. Next, compare this to a wedge-type gate valve that is 3/4 of the way open to flow with its corresponding LR/D value of 35. So in other words, valves fitted into a pipeline of a diameter of 1 would have an equivalent length, like an almost, it's an apparent length increase. So if you have a globe valve that I've just specified, the globe valve would act as if your pipeline was 340 meters longer in length, versus if you had the gate valve, it was 3/4 open, it would act as if the pipeline itself was 35 meters longer than what you've designed it to be. Okay, that's just to factor in efficiency. So just to be certain, we do not actually add extra pipe to pipelines when we design them. These values, LR/D, these are more like efficiencies or inefficiencies that we would add to our calculations. Okay, and these are actually then used to understand how flow is going to flow through the pipe, how the velocity is going to be affected due to the frictional losses incurred by these equipment. Okay, so don't worry, it will become as clear as mud very shortly. We will get into those calculations, but for now, lastly, just consider that pipelines are never straight. Pipelines are always skew, bent. They often require fittings to be put together. And so here are some more LR/D factors that factor in the resistance caused to flow by the twists, the bends, and the splits in flow that come about by using these different fittings. Okay, so we're going to go over fittings soon in this lecture, but in any case, let's quickly turn to Appendix 5 and look at an alternative. This is the resistance coefficient method. It uses a two-parameter equation to determine the frictional losses induced by the fittings and valves and other equipment. And it is the alternative to the LR/D method that we've just gone over. What you should take note is right at the bottom of the page, there's specific cases as well for pipe entrances and pipe exits, etc. Okay, so you'll have to factor these into your piping system designs as well. So, does my pipe have an entrance? Does my pipe have an exit? Factor in the pressure losses or the frictional losses due to these exits and entrances. This method requires you to have an understanding of the Reynolds number, as well as the diameter in order to calculate the equivalent frictional losses associated with these pieces of equipment. Same as LR over D. LR over D is equivalent to the K that you see here. K is equal to K1 over blah, blah, blah. That K value. Divide that by the frictional factor, F, and in essence, you end up with LR over D. They are interchangeable in that way. When calculating frictional losses in pipes, we will see how these equations, LR over D and K, actually fit into the calculations in a more specific way. So you'll more or less understand this in a better sense. We continue our discussion now on page 3 and into page 4. A variety of fittings are used to join two or more pieces of pipes together. Typical joints are 90 degrees elbow, 90-degree elbows. You have a long radius 90-degree elbow. You have a 45-degree elbow. We also have what you call a 90 as well as a 45-degree street elbows that both have that have both female and male threading at their ends, where the male parts screw themselves into the female orifices to complete the union. There are also three ways as well, which join three pipes into a corner, usually 90 degrees in geometry. And speaking of 90 degrees, we also have things like T-joints. T's are made up of three joineries, where one pathway is referred to as the soft T, since it causes the least resistance to flow because momentum is in the same direction always, while the hard T requires a hard change in momentum from a Y direction maybe to a Z direction or an X direction, and thereby it also is associated with higher resistance. How fluids flow through these T's must always be considered very carefully, because I'm going to try and trick you into applying this knowledge incorrectly. And in so doing, I help you to learn and understand. I'm also pretty sure that everyone has touched and handled cocks before. Cocks typically operate in their closed positions, and typically only when you require a sample of fluid do you need to operate a cock. Cocks, unlike other valves, are generally operated manually. You also get three-way cocks, and you may have seen these in the chemistry labs before, but if not, you most certainly would have handled both a hot and a cold cock at home. Along with the valves and fittings, we also have equipment, and equipment are also associated with their own resistances to flow. The pressure loss across pieces of equipment will need to be factored in when designing piping and processes. So typically, equipment you will come across as an engineer would be things like fluid movers, which are your pumps and your compressors, etc. You would have strainers, you would have screens, flow measuring instruments that sit in the path of the flow, consistency meters, and orifice plates, and maybe you lost a hand. That also causes resistance through the to the flow. But let's not talk about that. That's very dark, Ryan. Let's move on and talk schedules, and let's briefly discuss things like standards and piping systems that are used to standardize what we know as pipes. You will often see pipes and tubes that you buy accompanying certain specifications. This could be systems that these pipes have been tested against, like the ASTM standards, or it could be pipe formats, such as the materials of construction, the dimension standards, the tolerances, the percentage of alloys used, etc. So here is but one example of a pipe sizing chart that is specific to a Schedule 4 pipe. Pipe schedules are directly related to the ratio of the working internal pressure as well as the allowable stress. So it's the ratio between the working internal pressure and allowable stress for that material of construction for a specific nominal diameter pipe. So say we have a 10 millimeter nominal diameter pipe. The outer diameter for all schedules for the specific nominal diameter remain the same. And it is the internal diameter that is adjusted for according to the specific schedule. You can see that the specific schedules then relate to specific wall thicknesses, which in turn relate to a maximum working pressure. Now, dimensional standards. These are typically also provided to you in Appendix A1 for seamless and unscrewed steel pipes. I'll typically give you more information than what you need, again, to try and trick you and confuse you. So if you see something like a stainless steel 316L pipe, all you need to remember is go to Appendix A1. Don't let all that information confuse you. If it's a steel pipe, go to this appendix. In addition to this, you'll also find other information online from the manufacturer or the supplier of the piping. So if you don't see this, move along to another supplier. You should always make sure that you have this information available to you. If not, don't trust the pipe, don't use the pipe, get another pipe. Usually the diameters of the pipe will come with available ranges of wall thicknesses. And also each pipe's respective maximum working pressure or temperature will be given to you, specifically pressure. For example, as shown, a pipe with an outer diameter of, let's say, 25 millimeter has a working pressure range of between 180 bar for a wall thickness of 1.8 millimeter and 320 bar for a wall thickness of 3 millimeter. Note the shading as well for these pressures. The shading relates to gas service instead. Alright, so if you're using gases, those are the pressures that you're going to adhere to. If you want to operate at certain temperatures, you will always see information about temperatures and how to change these pressures given to you based on the operation, the temperature that you're operating at. Okay, so operating temperatures are usually given to you as allowed maxima as well, and these should never be exceeded. It is your responsibility as an engineer to make sure that such limits are adhered to for safety reasons. So please keep this in mind. Be responsible. Choose life, not death, and operate at the maximum temperature allowed. Alright, materials of construction are also given to you. Alright, and oftentimes pipes would correspond to certain applications, and so you would choose a specific stainless steel pipe, 304, 316, 317, whatever. Alright. And also you would also have a corresponding UNS or ASTM designation. For example, a 400 alloy will correspond to a UNS 4400 or an ASTM Monal 400 ASTM B163. All these codes are referring to is you are dealing with a nickel alloy. This alloy is commonly referred to as Monal. It contains roughly 2/4 nickel and 23% copper, and the balance will be some other, poor old metal that decided to show its face. Okay, ink alloy is another type of material or alloy that you'll come across in industry. It is typically a nickel-based alloy that has a very high strength and is resistant to elevated temperatures. One would typically use this with a turbine, for example, or a boiler, where you have very high temperatures that you'd be working with. Also, If you haven't seen this yet, I've uploaded for you onto ClickUp a comprehensive PDF containing all the symbols you would need when having to draw up your process flow diagrams and your piping and instrumentation diagrams in your final year, as well as for this module this year. This will most definitely be expected of you in your final year. So please, you better make sure that you know exactly what each symbol stands for and use the symbols correctly, or I myself will be asking you in your design reviews next year, when next I see you, what each symbol means. So, what exactly is a piping and instrumentation diagram? Well, it is a diagram. But more so, it contains all the process equipment, which are numbered and correspond to a specific legend. But please, 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 next year, if you're asked to draw a P&ID, make sure that your P&IDs are labeled specifically where the labels for the equipment appear right next to the pieces of equipment. Okay, so for the designs that you submit for CPJ 421, use the names of the equipment. This is the distillation column. This is the isobutyl propanol reactor. It is operating at whatever pressure and temperature. So usually with the pieces of equipment, you would have T equal 40 degrees Celsius, residence time 1 hour, pressure 40 bar. What is it? It is a reactor, etc. So however, in practice, you would generally just have a legend at the bottom in order to aid this, because you have a lot of information on these diagrams and they become very, very cluttered. So try just to make the communication as clear as possible, as brief as possible, and as correct as possible. Right, another thing to consider is the pipes that you are labeling. All pipes should be labeled for a pipe and instrumentation diagram. You provide the sizes, nominal diameters, materials of construction. If it's stainless steel, then it would be SS 304. And whatever whatever you often do to your diagram, something that would be done is you'd make a process stream that is the main primary stream thicker or bolder to distinguish it from other subordinate streams. It just makes it easier to follow the main process along. You'd also maybe use a long dashed line to indicate things like process steam, or maybe a dotted line, a dash and dot line for process water, cooling water, for example, and just be consistent and make sure that you've labeled these things. And as with reading a book, you must always draw your processes running from left to right, and never, ever right to left. Nor should you zigzag the process along the page, back and forth, and up and down, and in and out, and, go in circular fashions around and around. What you should do is draw the process only from left to right, break up the process into its different unit operations or process sections, and use new pages for each of the process runs that you are specifying. Never ever wrap your processes along the page. Okay, do this correctly and you will impress your examiners next year, including me. Identify all machinery, crushers, choppers, extruders, flash drums, poodles, you name it, literally name it, please, and use the right symbol. I cannot tell you how many times I have seen in design reviews a cutting mill being specified by some final year students, but I see on the page a hammer mill being used instead. So please make sure you use the right symbols for the right unit operations, because we will most definitely pick this up and ask you lots and lots of questions and hopefully embarrass you with the intention that you learn from it and that you know better. Moving on, process flow diagrams. 2, must specify all the process equipment. And again, try to avoid legends in your final year. You can have them, but also just remember, we have 10 minutes that we sit with you in your design review, and you need to convince us that you've done the best design compared to your peers. And it really helps to make your design readable. So when I see the reactor, I want to know this is the polyvanillin fluoride reactor. This is the pyrolysis or gasification reactor. Here I'm busy doing a Fischer-Tropsch. Here I'm busy doing distillation. Here I have a flash drum. Here I have a poodle, etc. And again, always depict flow running from left to right, not up or down, not roundabout in a circle. And mark my words, you will not listen to me and you will do this, and I will pick it up next year and you will frown at yourselves. You will be asked next year why you did not lay the process out properly, so please be warned. Weight all your lines according to primary and subordinate pipe flows, and also use the correct symbols. Please, please, please use correct symbols. And that is the introduction to piping system design. See you soon, guys. Use the right symbols, and always remember, use the right symbols.